Okay, I think we're ready to start the afternoon session. And our first speaker is Olivia Dumitrescu, who will tell us about how to go from the Hitchin component to opers.
I would like to thank the organizers for the invitation to speak. I would like to say this is joint work with Laura Fredriksson, George Kidonakis, Rafe Mazzeo, Motohiko Mulase, and Andy Netsky. It is started almost a year ago in AIM workshop organized by Laura Shaposnik and other people, and it was mainly motivated by a question of Philip Boge. And our aim in this talk is to describe holomorphic correspondence between a Lagrangian in the Dolbeau moduli space and a Lagrangian in the Dirac moduli space of opers. We will give a particular importance for the rank 2 case. So just to establish the notation, I will work with C, a smooth projective curve, and KC denotes the canonical. E and V are holomorphic rank R vector bundle over C. And for a Higgs pair, for a Higgs bundle, I will denote E and phi. And what holomorphic Higgs bundle, and what we mean by this is an R by R matrix of holomorphic differentials. For connection, we will use the notation via nabla, and it satisfies the Leibniz rule. And these are two examples in rank 2. So we are going to use, in particular, the first one that we were going to denote it by the Hitchin section, mainly any quadratic differential. Q is any quadratic differential on the base, and this will give us an example of a Higgs bundle. For what is important is that any connection locally on the curve C can be realized as the exterior differential plus A, where A is again a matrix of forms. However, it's very different than a Higgs field, and mainly they satisfy different rules with respect to the transition functions. So if F and G are the transition functions for the vector bundle C and V respectively, then the Higgs bundle is compatible with the transition functions, while A satisfies the gauge transformation. So in particular, it's not obvious if we start from a Higgs pair how to end up with a connection or reversibly. So this is what we're going to see in this talk, how to construct such a correspondence in a particular case. And I will remind motivation also was our work, what happens in rank 2 Higgs bundles. This is what we mean by a quantization theorem. So with Motohiko Mulase, what we did was to run the topological recursion formalism, and we discovered that a good setting is in the Hitchin context. So we use the same notation, but phi in this case can have possibly meromorphic entries. So in 2013, we discussed the case when phi is a holomorphic Higgs field, and we use a spectral curve constructed by Hitchin inside the cotangent of C. And the year after, we discussed the meromorphic case, and we constructed the spectral curve inside the compactified cotangent, and we constructed the resolution of singularities by blowing up this ruled surface. And what we discovered, the quantization theorem in rank 2, is that for any Higgs bundle, E and phi, locally on C, so X denotes a parameter on C, there exists locally a second-order differential operator, P of X, H bar ddx, whose semi-classical limit recovers sigma. So once we know the spectral curve sigma, we get our hands on an explicit second-order differential operator such that the second-order differential operator kills the generating function of free energies. And what this theorem does for us, our motivation was to make a connection between apparently two different worlds of Gromov-Witten theory and Hitchin theory by running the topological recursion formalism, while in the holomorphic case, it constructs the limit oper of Gauss conjecture. We're going to see that. So all the examples that we know happen in the meromorphic case, and this is something we will take just for our main rank 2 example, the Airy curve. So the base curve is P1, the vector bundle is half canonical plus half anti-canonical, And the meromorphic Higgs is this, with the meromorphic entrance. The spectral curve inside the Hirzebruch surface is locally the 0, 0 chart given by the characteristic polynomial. So mainly is y squared minus x dx squared. While if we move, this is a toric surface, and if we move along all the charts, to infinity, we find a quinticusp. And mainly what we do is to blow up this spectral curve and resolve the singularity, and sigma tilde denotes the proper transform. And in this case, it becomes a rational curve. So what topological recursion does for us, what the quantization theorem does for us, it finds a second order differential operator, h bar squared dx squared d over dx squared minus x, that kills the generating function of free energies. So this is the quantization part, and we also get a recursion. Mainly the free energy satisfy a recursion that can be solved, and this encodes the Gromov-Witten invariance of the point. And we mainly had, we were able to run few examples over P1 of meromorphic Higgs of rank 2, in which we find connections with Gromov-Witten theory or enumerative problems that we knew. So at that point, the question was that this at that point is not a globally defined operator, but is local. So we needed a way to make it globally defined, and for this we needed a definition of projective coordinate system. So from now on, in order to discuss Gauss's conjecture, we will look at Higgs fields with holomorphic Higgs fields. So this forces the Riemann surface to have genus at least 2. And its universal cover is the upper half plane. And this has a global coordinate upstairs, and the quotient map will induce a global coordinate on C. So this is a definition of Gunning in 67. A projective coordinate system on a Riemann surface is a coordinate system on which transition functions are given by Mobius transformation. And this is precisely what we mean by this. The connection between Z alpha and Z beta is done by a SL2R matrix. And in particular, on a projective coordinate system, the half canonical can be, the transition functions of the half canonical are linear. And this is something that we will use in the proofs of this. So the importance of Gunning's definition is that on a projective coordinate system, the quantum curve given by the topological recursion is globally defined. So this will be our first definition of opers, and we will come back to this for geometric definitions at the end of this talk. An oper, for now, will be a globally defined differential operator. So in particular, the quantum curve, when we restrict the case when h bar equals to 1, will be an oper as long as we work on a projective coordinate system. And we can interpret globally a second-order differential operator as a system of first-order system of equations. So an oper acting on this vector. And in the airy example, we started with this Higgs field, and this was the quantum curve. This quantum curve in a projective coordinate system, it corresponds to a family of oper, nabla h bar, that is d plus 1 over h times this matrix. And this matrix looks like a Higgs field, but it's in fact a connection. So it is a connection, but what is the corresponding vector bundle for this family of connections? And the solution comes from Gunning again. So we have to interpret h bar not necessarily as the quantization parameter, but as an extension class of line bundles. So namely, for any h bar complex, there exists uniquely a rank 2 vector bundle, VH bar, such that it's an extension of half canonical by half anti-canonical. So there exists this short exact sequence. And the proof that we're going to generalize is that VH bar is given by these transition functions. And we can notice that when h bar equals to 0, this is diagonal. So in particular, V0 is isomorphic to half canonical Dirac sum with half anti-canonical. While for h bar not equal to 0, then all these vector bundles together with the complex structures are isomorphic. So Gunning also proves that the moduli space of opers, of pairs, V and connection, is isomorphic to the space of quadratic differential. And in particular, this is affine. So it has an origin, and this we will call the uniformizing oper, We can add two uppers and obtain an upper. So what our quantum curve does, it realizes a correspondence between this Higgs bundle, in particular this Higgs bundle coming from the quadratic differential, to this family of uppers. It's a H-bar deformation family of uppers. And it's biholomorphic. So what we did is to start with a Higgs bundle, and we ended up with a connection. And this, in the general framework, in the Hitchin theory, has a name, and it's called the non-abelian Hodge that Laura Shaposnik introduced. So so for the rest of the talk, we will focus on the case of the Lie group G's SLR, and this forces E and V to be holomorphic vector bundles of rank R and degree 0. And in particular, the Higgs field has trace 0. So it's a holomorphic Higgs field with trace 0. So one realizes the Dolbeault moduli space as the moduli space of rank R stable holomorphic Higgs bundle C and phi, or the Dirac moduli space as a moduli space of rank R irreducible connections V and nabla, or the Betti moduli space as a character variety as representations from the first fundamental group of C to G, when G is SLR of C. So the Dirac and the Betti are biholomorphic, and this is a Riemann-Hilbert correspondence, while the Dolbeault and the Dirac are only diffeomorphic, and this was done by Hitchin and Simpson. So I will spend a few slides talking about this correspondence. Is this our quantum curve? And the answer is no. So this is the spectral curve of the Hitchin fibration that Laura Shaposnik also introduced as a characteristic polynomial inside the cotangent of C. And the Dolbeault moduli space is realized as a fibration of abelian varieties by the Hitchin map, where we just take all the coefficients of the characteristic polynomial and we made out a vector out of it, where all the entrants are just sections of the pluricanonical. So we will construct a section of this fibration of abelian varieties. And this is the Hitchin section, or Hitchin component in rank 2. So for this, we need to fix the spin structure C. And this is just a choice of the half canonical. And let us denote zeta, alpha, beta to be the transition functions for half canonical. Then the Hitchin map, in this case, just sends the Higgs pair to the determinant, because the trace is 0. While if we start with a quadratic differential on the base, the Hitchin section sends this quadratic differential into this vector bundle that it's split, and this Higgs bundle. And we had a look on this. And we can do this in higher rank. And here we will use a notation from the Lie algebra theory. If Q is just a pair, it's an element on the base. So the elements are sections of the pluricanonical. Let us denote Pi to be just a number, and X plus to be an upper triangular matrix given by the square root of Pi. X minus will be the transpose matrix, so will be lower triangular, while H is the commutator between X plus and X minus. So we associate a vector bundle that it's again split, E0, that it's a direct sum of powers of half canonical. And this in particular are given by transition functions of this vector bundle are given by this matrix H. Now the Hitchin section, for any element on the base, the Higgs, we will associate the Higgs pair given by the vector bundle E0, and the Higgs bundle will be a sum between X minus and powers of X pluses. So this will be a basis of the nilpotent element with coefficients Qi, the spectral data. And this in particular is a stable Higgs pair. So it's an element of the Dolbeault moduli space. Now, we started with a holomorphic Higgs bundle, but as Laura introduced, the original definition was in fact a pair D, phi, and H, where the H is a Hermitian matrix, D is an H unitary connection, and such that this satisfies Hitchin's equation, that it's a nonlinear system of PDE, obtaining from a reduction of Yang-Mills theory. So FD denotes the curvature of this connection, while phi daga denotes the adjoint of the Higgs field with respect to the Hermitian matrix H. So the first equation, the second equation gives the holomorphicity, that phi is holomorphic Higgs, while the first equation gives the stability condition. So phi is a stable Higgs bundle. So these Hitchin's equations are equivalent to the flatness of a family of connections. So zeta is a complex parameter, and d of zeta is 1 over zeta phi plus d plus zeta phi daga. So the non-abelian Hodge, it starts with an element on the Dolbeau moduli space, and it associates to this a connection where V is the same vector bundle E, but with a different complex structure, is the one that comes from D of 1, from the anti-holomorphic part of D of 1, while the connection gives the holomorphic part of D of 1. So as we mentioned in the previous slide, this is a diffeomorphism. So it was not the quantum curve or the oper that we associated. So we had to then look for more possibilities on how can we make sense of this association. So now I will mention a few words about Gayota's conjecture. So we start with an element of a Hitchin section. E0 is split, and phi of q is constructed as a sum of x minuses and x pluses with different powers. And we twist by r, a real parameter, positive. So in particular, this element that we find is also stable. So it's an element of the Dolbeau moduli space satisfying the Hitchin's equation twisted by r. So the solutions of Hitchin's equations, again, correspond to the flatness condition of a family of connections that depend on two parameters, zeta, that is complex, and r, that is real number positive. So d of zeta and r are just a twist by r in the Higgs field. In 2014, Davide Gaiotto predicted that for a Higgs bundle on a Hitchin section, then the limit when r and zeta approach 0 with a fixed ratio, and this fixed ratio is h bar, of d zeta r exists and is an oper. So before we say more about this, it is not obvious why this limit should exist, because in particular, this when r goes to 0, when r approaches 0, this term blows up. So the Hermitian matrix blows up. So it is not obvious why this should exist, or it will be an oper. So let us see what happens at least in rank 2. Well, in rank 2, we identified an oper as a connection with a condition that V comes from a short exact sequence. And we should interpret this short exact sequence as a filtration with two terms, where this is the first element of the filtration, this is a second element, and with fixed ratios, this is the last element. So the opers in rank R are defined by Bayes-Son and Drinfeld on a holomorphic vector bundle, V. An SLR oper is a connection with a filtration such that it has r plus 1 terms starting from 0. It has the Griffiths transversality condition, and it has fixed ratios. So it's an isomorphism twisted by the canonical. So we can now generalize the Gunning work, and mainly there is starting from the line bundle half canonical to r minus 1, there exists a unique filtration and the vector bundle, and the unique vector bundle VH bar. And in mainly VH bar, this one parameter family of vector bundles is given by the transition functions that are product of exponential matrices in this form. And when h bar equals to 0, what we find is just E0, that we denoted the direct sum of half canonical to certain powers. While for h bar not equal to 0, then all these vector bundles, together with their complex structures, are isomorphic. So on this family of vector bundles, we can now define the connection nabla h bar to be just the external differential plus 1 over h bar times the Higgs field phi of q. So this is an element on the Hitchin section. And it is not obvious that once you start with a Higgs field and you do it in this, and you plug it in this formula, you'll obtain a connection, but it happens in this case because VH bar is a deformation of V0. So the claim is that VH bar and nabla VH bar is in fact a family of opers, one parameter family of opers. So the result is that Guyotto's conjecture holds, and this is a theorem by Laura Fredriksson, George Kidonakis, Rafe Matsumoto, Hiko Mulatsky, and Andinetsky that will be posted soon. So mainly the limit when R and zeta approach 0 with a fixed ratio, this family of connection exists and is the opera that we just constructed. And this works for SLR and for any arbitrary simple and simply connected Lie group G. And what we've just seen in rank 2 is that the limit upper of the given by topological recursion is in fact the limit upper of the Guyotto's conjecture. So what this Guyotto's conjecture does, it realizes a specific natural canonical biholomorphism between a Lagrangian formed by the Hitchin component and the Lagrangian in the Dirac moduli space given by the moduli space of opers. So in the next slide, I'm going to say a few words about the sketch of the proof in rank 2. And in rank 2, what happens, well, it's important to observe that the canonical bundle has a canonical matrix that comes from the downstairs curve C. And in particular, the Hermitian matrix that is induced on a vector bundle, that it's a split bundle between half canonical and half anti-canonical, is given by the conformal matrix. So it will be a matrix H, the form lambda inverse and lambda, diagonal matrix, when lambda is a real positive real valued function. And the D, the connection bit becomes the Chern connection associated to the Hermitian matrix, and it has this form. And once we start with a section on the Hitchin component, then phi daga is just it is disassociated Higgs field. So the flatness of the family of the flatness condition, the family of connection D of zeta and R gives the harmonicity condition for nabla, for lambda. So lambda is a positive real valued form such that it satisfies this PDE equation. And this imposes strong conditions on lambda, in particular when p equals to 0. So when p equals to 0, then this Higgs field was just given by the matrix X minus, what we call X minus. One can solve this equation. And solving this harmonicity condition, one obtains that lambda 0 is just this conformal matrix of constant curvature minus 1 on the upper half plane times 1 over R. And the observation is that now it's obvious, for example, that the Hermitian matrix blows up when R approaches 0. It's not quite obvious how to take that limit. However, in general, this is the connection between lambda and lambda 0. So exponential is just a conformal change of constant curvature matrix. And lambda is giving a solution of the with a harmonicity condition with analysis using an implicit function theorem on the Banach space. One proves that f is a real analytic function of vanishing order 4. So plugging in the flatness condition of D, and one can take the limit carefully in this expression and observe that in fact this converges. And the limit opera, it is gauge equivalent to the opera that we just constructed. So this is a sketch of the proof in rank 2. And before we end the final picture, here we have the moduli, the Dolbeau moduli space of holomorphic Higgs bundles. And it's a fibration, and the green Lagrangian represents the moduli space of, well, includes the moduli space of stable bundles, is the fiber over 0. And this is the Lagrangian given by the Hitchin section, and it has a natural origin that we denote E0 and X minus. So this is on the Dolbeau moduli space, while on the Dirac moduli space, we see, well, we have the non-abelian Hodge correspondence. And by the non-abelian Hodge, the moduli space of holomorphic stable bundles is sent by the Narasimha-Seshadri to the moduli space of unitary flat connections, while the Hitchin section will be sent to the what is called the Hitchin component, and this is red Lagrangian. While Gayotto's correspondence realizes a canonical biholomorphic map, and the image of the Hitchin section, the red one, it becomes the blue. It is the moduli space of opers, and it has additive structure, and the origin of this is given by the upper corresponding to, Q equals 0 is V1 and the D plus X minus. So this construction is one by one, is point by point. And it's bicolomorphic. In one direction is the, well, in our sense, quantization. In the other direction is the semi-classical limit. So this is mainly the result. And I would like to thank you for your attention and to promote the interactions between geometry and physics. Thank you.
Thank you very much. Are there any questions?
Vincent.
So I don't know how much you use that in your proof of, you probably don't use that in your proof of Gayotto's conjecture, but if you have a spectral curve which is genus greater than 0, and you use topological recursion to construct your psi, then the quantum curve will not be what you said. It will have an infinite number of h-bar corrections that you can calculate explicitly, but it won't be 0, for sure. So I don't know.
I mean, you want to say that you have some perturbation in the quantization?
So the operator that will kill the psi will have an infinite series in h-bar. And you can calculate every term explicitly.
And this in higher rank, you mean, in the...
Rank 2.
In rank 2 as well?
Yeah. Which we can prove explicitly. And you can check on Mathematica and so on. But I don't think you use that actually in your proof, probably, of Gayotto's conjecture. But that's just a remark. We can talk about it if you want.
Okay.
Okay, are there any other questions? Comments? If there are no other questions, let's thank the speaker again.